Welcome to my website. I'm Matthew Polkassar, and the title of my dissertation is Simulation Models for Control using the Modelica Dymola Environment, and I was supervised by the engineer Marvin K. Bugeya. The objective of this project was to design 4 different inverted pendulum control systems, and they were modeled using Dymola, a commercial front end for Modelica, which is an object-oriented language. It is a modeling language, it is a declarative language, and it is also a general-purpose multi-domain. It is a general-purpose multi-domain because of the fact you can model a motor that has both electrical and mechanical appliances. It is also declarative because when one types V equals IR in Modelica, it can either have I and R and you get V. You could either have V and I and you get R, and you can either have V and R and you get I. While in other imperative or structured languages like MATLAB, when one types V equals IR, it only obeys that you have I and R and you get V. The 4 inverted pendulum considered are 1. The inverted pendulum monocard, which is also sometimes called the card pole inverted pendulum. 2. The rotational inverted pendulum, also called the Furuta pendulum. 3. The pendubot. And 4. The inertia wheel pendulum, also called the reaction wheel pendubot. These inverted pendulums are underactuated. In underactuated you have one motor controlling 2 things. Generally you have one motor controlling a thing, and another motor controlling another thing. In underactuated you have one motor controlling 2 things. The main objective of this project was to design 4 complete control strategies of these inverted pendulum systems and modeling them with Modelica Dymola, and to create a 3D animation of these controlled systems. The methodology used for this project was first to derive the dynamic mathematical model of each system. It could be either using Newtonian, which uses the principles of dynamics, or using Lagrange, using the principles of energy. Then the modeling the plants using Modelica Dymola, component-based approach, and then the verification and comparative analysis of results using Modelica Dymola and MATLAB Simulink, using an equation-based approach. Swing up and stabilizing control algorithms were designed from scratch for 2 of the systems that were the pendubot and the inertia wheel pendulum, and for all of them the complete control systems were implemented using Modelica Dymola. Modelica has certain advantages. One of the advantages is that you can see how the system behaves without deriving the mathematical model. Let us consider this system, which consists of a spring, another spring, and another spring. This system consists of 3 springs. One of the springs is connected to 2 other springs. There is the pendulum, the revolute joint, and a bob, another mass. With Modelica, one can see how the system behaves without the need of deriving the mathematical equation, because it is declarative. As one can see, the system is very chaotic. Also, there is an advantage, because when people try to derive the transfer equation, they try to take certain assumptions, like, for example, the system is symmetric, in order to derive the transfer function. In this case, for example, the stiffness constants of the elasticity is not equal, therefore the system is not symmetric, and therefore people tend to take certain assumptions, and that when deriving the transfer function it is not accurately done. This could be done because Modelica is acausal, while other programs like System Build, MATLAB Simulink, EZ5 and ACSL are causal. An acausal does not require for the equation to be transformed into a state space form, while in causal the model needs to be transferred into a state space form. In a causal, the equations can be written in differential algebraic loop. That means that it avoids the restriction against the presence of algebraic loops or implicit nonlinear equations, while in causal, the equations can be written also in ordinary differential algebraic. As one can see, a causal is more component based, while in causal it's more block oriented. In a causal there is no need to transform the transfer function, while in causal you need to transfer the transfer function. Also, one can note that if a resistor is changed into an inductor, for example, in a causal you only have to change that part, while in causal the whole transfer function must be made, it must be changed, and therefore the whole situation has to be changed completely. It is important to note that in a causal, one must identify the true and the cross variables. The true variables, like for in our case the circuit is current, are those variables that at the summing point B, at the node B, the summing point is equal to 0. While the across variables are those variables, in our case the voltage, that if the system is cut, the variable, in our case the voltage at the left hand side is equal to the voltage at the right hand side. The first pendulum considered is the inverted pendulum on a cart. Here is the pendulum which is attached to the cart, and the cart moves horizontally. According to the movement of the cart, the pendulum oscillates. The cart is also bounded in the horizontal distance. Here are the nonlinear open loop dynamics, which were derived using both Newtonian and Lagrange. Here reference was made to Marvin Bourgeois nonlinear swing up and stabilizing control of an inverted pendulum system, done in the University of Malta, May 2002. And there are two controllers. The swing up controller, which is a nonlinear controller which swings the pendulum from the downward pendant position to the upward position, and the stabilizing controller, which is a linear controller and it only behaves at the neighborhood of the upward position. The swing up controller, first the mechanical energy is derived. Its derivative is computed, and consideration must be taken that its derivative must be always positive, so that its mechanical energy is always increasing. And also it was taken into consideration that the cart was bounded. The stabilizing controller used was pole placement with 4 poles, with the dominant closed loop poles having a high damping ratio of 0.9 and an oscillating of frequency of 4.5 radians per second. From the graph, the red is the angle of the pendulum and the blue is the distance moved by the cart. Worth noting that the maximum distance moved by the cart is plus or minus 0.7 meters. And this could be seen also from the 3D animation, where the red is the cart and the blue is the pendulum is getting swinged up, and right now it's stabilized.